In this video, we're going to discuss moment of inertia. Now, inertia, well, that's a physical object that has mass. It's the tendency for it to resist any change in motion. And a moment of inertia is then linked to rotational motion. And a moment of inertia is kind of like the rotational motion's equivalent of what mass is to linear motion. If I discuss an example of something rotating about a point, so I'm moving in a circle, so I've got a mass that's going to be rotating in this circle of mass m, and the distance from the centre to the mass is r, and it's going to have a linear velocity v and an angular velocity omega. And in previous videos to do with circular motion, we discussed the link between linear velocity and angular velocity, and it is v equals r omega. Okay. And what we're going to talk about is the kinetic energy this has. Okay, in terms of linear motion, the kinetic energy is equal to half mv squared. But if I were to replace the velocity v with r and omega, so if I just place this in here, we're going to get half m and then r omega squared. And if we square all that, we'll get half m r squared omega squared. And it's this term, mr squared, that is what we call the moment of inertia. And it's given the symbol capital I. So kinetic energy is half I omega squared. That's an equation for kinetic energy in terms of rotational motion. And if we talk about the kinetic energy it has in terms of its linear motion, that would be half mv squared. So there's similarities. The linear velocity, the angular velocity, this is our kind of mass in terms of linear motion, and this is our mass in terms of angular or rotational motion. And this is what we're going to be discussing today. It's this moment of inertia. So what we're going to do now is we'll talk about how you calculate that, because it's not just a simple case that it's always mr squared. So in this case it is, where you've got this this small amount of mass, a distance r squared away, but you might not necessarily have just a chunk of mass one distance away. Okay, so there are a number of different scenarios that we can go through to help explain what I'm talking about. And the first thing to do is, if we can expand on this and just talk about two masses rotating about a point. So we've got mass 1, and we've got mass 2, and they are going to be rotating around this central axis of rotation. The length between these two masses is L, and then that would mean from the centre to that mass would be half L, and from the centre to that mass would be half L. And so before, when I said that I equals mr squared, well, the moment of inertia of a system of more than one mass is just simply the fact that we take our masses, each one of them, okay, in this case there's only two, but I number of, and then we multiply the I number of those masses by the distance ri squared, and we are just simply summing up all these masses. Okay, so that's what we're going to be doing. We're going to be taking however many masses there are, multiplying by the distance it is from the centre of rotation squared, and then we're just going to add them all up. So in this scenario, we've simply just got 2, and so we're going to do m1, and that's going to be a distance r1 squared away, and we're going to add m2, and that's going to be a distance r2 squared away. Just expanding upon that, r1 we've suggested, so if this was r1, we're we've suggested that's half the length between the two. And then likewise R2, that's also going to be half the length. So we've got M1 L over 2 all squared, and then M2 L over 2 all squared. And that would come out as M1 L squared over 4 plus M2 L squared over 4. I could just slightly rewrite that as M1 plus M2 L squared over 4. If M1 and M2 are equal, so if we said that mass 1 equals mass 2, and I'll just say that's M, I can replace M1 and M2 to just say I've got 2M, and so in this system, if it's the same size masses, I would equal 2ml squared over 4, which is ml squared over 2. Okay, so this is the moment of inertia then for two masses. If those masses are different masses, then there's the expression. If, however, they're the same mass, then here's the expression. Okay, so that's pretty straightforward. We did one mass, we've done two masses. But then we can start to look at many masses, okay, about a point. Or we could look at potentially a shape, some complicated shape like this, and that could be rotating about this axis of rotation. And what we would do to work out the moment of inertia, like discussed before, is we would sum up lots of parts of mass a certain distance away. So we could like break it up into tiny bits of mass, and whatever that mass is, let's call it M1, it would be a distance R1 away. Whatever this mass is, M2, a distance R2 away. And in each case we do M times R squared, and then we would add all of these pieces up until we've covered out the whole of this shape, and then we'd find the moment of inertia for that shape. But what we can do is we can actually integrate over the whole shape. So I'll do that with an example. The example is going to be a uniform rod, and this uniform rod we are going to have it rotating about its center. Okay, so here's a rod. And it's going to rotate about its center, and we want to know what its moment of inertia is. Here's some physical dimensions to the rod. The rod is L in length. Okay, and as we said before, we would just be looking at breaking this up into amounts of mass, finding the kind of part of the moment of inertia for the mass, that mass a certain distance away squared, and then add them all up. Okay, but what we've suggested is what we can do is we can integrate across the whole shape, and when we're integrating, we're going to integrate over an infinitesimal amount of mass, so we need a small amount of mass. So here is kind of an element which has mass m in it. It's very, very small. So there's delta x in thickness, and it is a distance x from the center. Okay, so what we need is we need to kind of put this in terms of the overall mass of the object, which I'm going to call big M. And if I were to think about the ratio of little m to big M, so the ratio of the mass of the small element to the overall mass, that should be equivalent to the same ratio as looking at dx over L. Okay, just to make that easier to understand, if I took the entire rod and I cut it in half so that my element was half of the overall mass, then dx would be half of the overall length. And then if I rearrange that for m, I get this expression. Oh. Okay, and then if I were to just look at the moment of inertia for that little element delta x, then it would be the mass big M over L dx, delta x, and it would be multiplied by the distances away squared, so that's x squared. Okay, so I've now got an expression for that small element, and now what we're going to do is we're going to integrate throughout the rod, adding up all these small elements a certain x away. Okay, so what we're going to do to find out the moment of inertia of the rod, we're going to add them all up, or we're going to integrate. Now what we're actually integrating from is, if we call this 0, and we're going to integrate up to L over 2. That length is L over 2. And we're integrating this, this, but we'll turn this into an integral form by saying that we're going to integrate in terms of this small x, so in terms of x. And the other thing to point out is that is only finding half of the moment of inertia of this rod, so this would be twice that. Okay, so this is not a discussion about how to integrate, but what we can do is we can pull out anything that's not in terms of x. So m and l are constants and don't change, they're not a function of x, so they can be pulled out, and then it's just the integral from 0 to L over 2 of x squared dx. Okay, and then that comes out as x cubed over 3, and if we put these in, we'll have 2m over L over 2 all cubed over 3. Take away 0 cubed over 3, which is 0, so we'll just leave it at that. And then what we come out with is L cubed, and that would be over 8 over 3, which is then 2m over L cubed over 24. And then we can cancel the L top and bottom, and then we can cancel a 2 down here to a 12. And what we find is the moment of inertia for a rod that's rotating about its centre is equal to ml squared over 12. Okay, so it's the mass of the rod times the length squared divided by 12, and that's the moment of inertia for a uniform rod rotating about its centre. Now, a slight difference. We can look at the rod again, but this time we're not talking about it rotating about its centre. This is going to be a uniform rod rotating about one end. Okay, so it's going to be rotating now here. Okay, so the entire rod's moving around, and that's the axis of rotation. So as before, you've got the length of the rod L, and then what we're going to do with that is we're just going to do the same integral as before. So we got to the point where we said that the moment of inertia of the rod would be, I pulled out m over L, and then we were going to integrate, but before we integrated from 0 to L over 2, it's now just going to be from 0 to L. Okay, so from this point, integrating outwards, summing up all the masses times the distance squared from that axis of rotation, and it was the same terms as before, x squared dx. Okay, so integrating that, m over L, x cubed over 3, and then putting L into there, taking away 0 cubed over 3 would just give us m over L, and then that would be L cubed over 3. L cancels down at 2, and so this time you get ml squared over 3. Okay, so slightly different this time. The moment of inertia of a rod when it rotates about its end is ml squared over 3. Okay, next example, is looking at a flat ring. Okay, so here it is. So okay, so this ring has mass m. It's going to be rotating about the center, and as before, we can think about a little element m, but every single little element m is always going to be the same distance away from the center of rotation. So it's fairly straightforward to work out the moment of inertia of a ring, because if we were going to sum up all the little element masses times their distance away squared, what we're essentially going to end up with is the total mass of the ring times the distance away squared. And that's because the total mass, if we were to sum all these up, we would get, if this was m1, then we've got m2, m3, m4, m5, all the way around. If you add all these up, however many you break it up into, you're just going to get the total mass m of the ring. So the moment of inertia for a ring is just the mass of the ring times x squared. We can leave it as x squared, we could say maybe the radius squared, but I'll leave it as x squared. Okay. Now what we're going to look at is not just a ring, but an actual disc. Okay, so if we look at a disc, this is now a disc. Okay, a little trickier, but if we think about it in terms of the ring, but many rings. Okay, so if this disc was rotating about its center, and we looked at the moment of inertia of part of it, of the disc. But if you think about integrating out, working out these rings and summing up their moments of inertia across the entire disc, we can then find the moment of inertia of the full disc. So let's put some information in here. So this time what I'm going to say is that the thickness of the disc is dx. In fact, let me just draw this again and make it bigger so we can see what I'm talking about. Okay, so this disc then is of delta x thickness, and the entire radius of the disc is r, and then the distance that this ring of mass that we're going to be working out is a distance x away. And we can start by looking at like with the rod, we can look at the amount of mass that this ring has compared to the entire mass of the disc, and then we can come up with a ratio that also looks at the ring's area to the disc's area. Okay, so we're going to do what we did similar to the rod, except for the rod was in one dimension. This is now, so that was like a length. We were comparing little m to big M with the small x to the length, and now we can actually compare the area of the ring to the area of the disc, and that will also give us the same ratio as looking at the mass of the ring to the mass of the disc. So if we look at the mass of the ring and compare that to the area of the ring, and we divide that by the mass of the disc and compare that same similar ratio. Okay, and what we're going to get is a term where we can have little m in terms of big M, but also the physical dimensions of our ring and disc. So the area of the ring, okay, if you think about the outer part of the ring, and then so you worked out an area of a circle, and then you worked out the area of the inner circle and took that away from the outer circle, you're going to be left with the area of the ring. So we're taking the area of the outer circle, which is x plus dx. So we've got pi x plus dx delta x squared, and we're going to take away the area of the inner disk, which is pi x squared. We just need to expand this, so we've got x squared plus x delta x, but then another x delta x, so we'd have 2x delta x, and then the delta x squared. Okay, this is an interesting thing, that if you've got a so remember this is a very small number, and you square that, you're going to get an even smaller number. What do I mean? Well, if you think about, if you had 0.1, okay, and you square that, well, what you're doing is you're squaring a tenth, which comes out as 1 squared over 10 squared, which is 1/100th, which comes out as 0.01. So in other words, squaring a small number, a decimal number, a fraction of a number, you're going to get an even smaller number. So this can be thought of as being very close to 0. Okay, so expanding that bracket out, squaring this, we're going to suggest that the number that we actually get out is going to be x squared plus 2x delta x. So the area of the ring, multiply this whole thing by pi, you're going to get pi x squared plus 2x pi delta x, 2x pi delta x, and then we're going to be taking away pi x squared. Well, if you've got pi x squared and you take away pi x squared, there you go. And then so the entire area of the ring is going to be 2 pi x delta x. And then the area of the disk is more straightforward than that. It's got a radius r, so that would be pi r squared. Okay, now we can, as we did before, rearrange for m. So we've got m equals 2 pi x dx over pi r squared times m. And now what we're going to do is we're going to think about this in terms of the moment of inertia, which would be our mass m times r. In this case, that mass is x away, so x squared, and m in terms of all this is 2 pi x dx over pi r squared m, and then we're going to times that by x squared. And then I'm just going to turn to the next page. Try to keep that kind of in shot for now. So this, if you just remember this, I'm going to rewrite it now at the top line here. So we've got the moment of inertia, just thinking in terms of just that very small ring within the disk, is going to be x delta x over pi r squared m x squared. We've got an x here, we've got an x squared there, so it's going to come out as 2 pi x cubed delta x m over pi r squared. And then we've got pi top and bottom, and so our expression now is 2x cubed delta x over r squared m. And so this is the kind of thinking about the moment of inertia, just that small amount of mass. But what we want to do to find the entire moment of inertia of the disk is we want to integrate all of these little bits of mass with respects to the distance x. Okay, so going back to our disk of radius r, we want to integrate from 0 up to r, and we're going to integrate this, turn it into an integral, just to say infinitesimally with respects to x. So we've got 2x squared, cubed, over r squared m dx, and then we can pull some of the terms out because they are not a function, they do not change in terms of x, and that would be m and r squared, and the 2. So we've got 2m over r squared, and then it's the integral of x cubed dx from 0 to r. Okay, so hopefully you've understood what I'm trying to do. I'm trying to work out an infinite sum of all this mass of an individual ring as it grows out from 0 to r. Okay, so it stays the same, and then if we do integrate that, you're going to get x to the power 4 divided by 4 between r and 0, and then obviously r goes in here, 0 goes in, and you'll be taking away nothing, so you're left with that times r to the power 4 over 4. And then we can cancel an r squared below and an r squared above. We can cancel a 2 and a 4 here down to a 2, and so we're left with big M r squared over 2, and that is the moment of inertia of a disk. Right, okay, so we've come up there with a number of moments of inertias of certain shapes, and just to recap, we looked at the moment of inertia of a disk, the moment of inertia of a ring, which is just m r squared, and we also looked at the moment of inertia of a rod, but about its rotating about its center, which came out as ml squared over 12, and then the moment of inertia of that rod, but it rotating about its end, and that came out as ml squared over 3. Okay, so hopefully you've managed to follow that. As always, I'll do some exam style questions which massively help, because you can actually see all of this theory in action with some numbers, so hopefully that'll clarify anything that has been difficult to follow.